Uh, Hi everyone, I'm Jiatao. I'm from HKU. Today I would like to talk about Trainable grid decoding for neural machine translation, and this is a joint work with Joe and my supervisor Victor Lee. Okay, let's start with everyone knows about neural machine translation right now. So the neural machine translation model is basically a model is the condition probability given a source sentence X over the target sentence Y, and which can be decomposed as an autoregressive way into and where each component is also modeled as a encode-decode fashion. So we can see in the right-hand side, so there's a model where we usually define the neural machine translation. And for training, so people are usually using the maximum likelihood estimation, which is essentially maximize the ground truth translation Y at each time point, given the source answer X, and it can be trained quite efficiently given enough translation pairs. But it is notable that the MLE does not take into account how, after a trained model, how can we use it. So to have a model, when you use it, we need to have another algorithm called decoding for really have a translation. So ideally, what we want to do is actually the maximum a posterior estimation. That is, we want to find the translation Y that really maximize the log probability of given the sentence X. However, it is unfortunately intractable because the computational complexity is exponential of the sentence length. So we need to do a trade-off. So in practice, approximate can be made something called grid decoding. So the grid decoding, the simplest way is to find each time step gets the word with the largest log probability, and take this word as the next, send it to next step. And as I can show on the right-hand side, where I use y hat as the word generated by the model to be the grid decoding. And of course, the grid decoding is obviously suboptimal. So we need to have a better way to do this. Somehow we called a beam search. So when we're doing beam search, we at each time step, we will keep not only one hypothesis, but k hypothesis with the highest cumulative scores. And when all the hypotheses terminate, it will return the hypothesis with the highest scores. So it is a better way to to find a better translation sequence. It will always have a better score compared to grid decoding, but unfortunately, the computational complexity grows linearly with the beam size. So here comes our motivation. So in general, what our research is doing is to find a better neural machine translation model to solve the machine translation. And to do so, people usually have different research directions. And most of the direction will be focusing on the model selection. For example, right now, people are usually using the sequence, maybe the standard way, and maybe add a little attention, a little deeper, or maybe we get rid of recurrent network, and we can also maybe add more syntax and more other features. Now, all these selections are trying to model the data to really reflect the reality of machine translation. Another way is to focusing on the training algorithms. So given a model, how can we train it more effectively to use it? For example, we mentioned the MLE, but which is maybe not the best one. We can also using like minimum risk training or reinforcement learning to train a model. However, there's not so many papers are talking about the third way, is the decoding itself. So is really, can we find a better decoding method that is suitable for any kind of objectives? For example, an algorithm as efficient as a grid decoding, but have a better approximation results, such as a beam search. So that is the focus of this talk. For the motivation too, and is that the default decoding objective is also not the best one we choose. Even for the MAP estimation is not only the desirable decoding objectives. For example, actually we are always evaluating translation use Bruce score, not using the perplexity or using the log likelihood. And we also can using human rating to have the translation result, which is somehow not very different from what we are training. Another way is maximizing the local conditional probability at each time step, as what we did in grid decoding is not necessarily maximize the global probability, which is the main weakness of grid decoding and all other grid decoding methods. The third thing is maybe our hope is to have one training model but can apply to many different objectives. For example, we train a model on a very big data set, but we can decode it for many different purposes. For example, readability, accuracy, latency, or styles. Or we can use the trained model applied on different tasks. For example, we can use a trained model applied on real-time translation. At that time, our target is not the quality at all. At that time, we are focusing on both the quality and the translation delays. Then, in that case, should we always train a different model for different objectives? Maybe our choice is to have one model, but decoding in different ways. Then we come to the trainable grid decoding. But before introducing our method, our model is heavily inspired by one previous work is called noisy parallel approximate decoding. And requested by the first author, he asked me to say it's rejected by NIPSI. but of course, so the main idea of this one is different, but it's to find a better translation by injecting unstructured noise in the grid decoding algorithms. So it's actually, I can think it's a first work that is trying to control the decoding algorithm itself by adding things into it. So here, all the noise epsilon t is sampled from Gaussian distribution, and this model can work better than grid decoding when we have a lot of different chains running in parallel, and we can always find a way to get a better choice. But this method is great, but can we always doing this though? Because running all the chains in parallel is quite costly. So can we make the injected noise trainable to avoid the parallel sampling? So a naive way is, okay, so just replace the noise by a function, a parametric function parameter, or we call it an actor. So here we replace the noise with an actor, which we can use simple feed-forward networks. At each time step, the network will receive the decoded hidden state, the context vectors, and the previous words, and output a real valued vector action, which is, instead of using a noise, just an action, add into the hidden state. And the function is deterministic. So why we use this one? So our model, our algorithm trainable decoding model is to train this actor that maximize a certain objective for pre-trained NMT model. And after train the actor, we can run the grid decoding algorithm with this actor's output and to have a different objectives. The next question is how to train this actor. So one thing we mention is we only need to update the parameter of the phi, which is actor. We don't need to change the original model. That is to ensure the generality of the pre-trained transfer model will not be ruined by our algorithms. And also it allows us to train in multiple actors with different objectives. So it's the one training for many decodings. And then the objective is quite trivial. So it's just to maximize the expectation of attribute decoding objectives of R. So here we use G pi x to denote any decoding process, and D is our training data. So we always sample X from D, and using our current decoding method get Y, and have the expectation of that. Then we come to the challenges. So there's two main challenges. First one is the objective R may not be differentiable with respect to the actor, which is a common case because, for example, we're using Boost score that is normally not non-differentiable, or we can use in other scores. And we cannot train the actor simply through backpropagation easily. Another problem is more difficult. That is, our actor is designed to output a real valued deterministic policy that have in a very high dimensional action space. It's almost 1,000 dimension, which is well known to be difficult to optimize. To tackle on that one, we first introduced to using reinforcement learning to train the actor. Here we specifically using deterministic policy gradient. So to use the deterministic policy gradient, we need to design another network called, which is a parametric differentiable estimator called a critic to predict the objective, or we call it a return. And to train this critic, we simply to minimize the outputs of the critic and our real return. In our implementation, the critic can be a recurrent network with each hidden state of the model and perform the prediction in the end of the last hidden state. Then our learning objectives switched from maximizing the exact objective R to its approximate RC. So we train our actor based on the to maximize the output of the RC. Here is a visualization for this model. So we have the actor receive each time step receive the hidden state from the original model and predict the actions at each time step. And the critic will also read the hidden state of the original decoder and each step by step until the end it will predict the RC. And there's two optimizations. One is to train to always make the critic catch up with the real objective, and then the actor will be trained based on the output of the critic and to make it better. These two optimizations are performed alternatively. So let's come to the next challenge. So actually, it's the difficulty of optimization. The first we need to think about, is it really possible to do a reinforcement learning in such high dimensional space? Because in our experience in reinforcement learning, the highest dimension may be 50 dimensions or 40 dimensions. But in our case, maybe yes, because the state space has already been well structured thanks to the pre-trained MLE. Because we are not from scratch to train 1,000 actions, but it's depend on the hidden state. The action works as a very tiny perturbations on the hidden state, and mostly will leading to still a reasonable translations. That will mean that if I run 1,000 different actions, we can have 1,000 different translations, which is still reasonable, and we can get 1,000 different rewards. So in that case, it will turn the very sparse reward problem still become a dense reward problem and make it trainable. However, even we doing this one, the searching space didn't shrink. It's still a very difficult searching optimizing problems. So talking on that, we further using techniques to make it stable. Here we propose a method called the critical aware actor learning. Here and before we talking about that, we need to think back. The major goal of the critic actually is not to catch up with the output of reward. So although we trained it to minimize the L2 distance, but actually the goal of the critic is to estimate the gradient of the evaluated objectives, because the critic will always pass the gradient back to the actor and train the actor. So to do this, the critic need to know if I change a bit on the actor, the actor's output change a bit, how much it will change on the reward part. In that case, we can predict the gradient well. And in order to do these things, we need to have a better exploration method on the actor space, action space. Otherwise, it may be leading to a very unstable way in the actor learning. So to do this, first we inject the noise, which is also introduced in the original deterministic policy gradient. So instead of using, Aside of using the action, we also add the noise into the actions, which have the same dimension with the action itself. And the action, currently, the noise is sampled from the Gaussian noise. In practice, to reduce the valence, a pair of noise are used. So when injecting the noise, we also find it useful to make a grid-aware grading estimation. So that is to say, we will our grading to update the actor will be infected by the critics confidence. The intuition is to find the directions in the actor space for which the critic thinks is that is good. Then we go that way. And the effective rate can be achieved by using importance sampling to reweight the gradient estimate based on the quality of the critic's output. Here is a figure showing that if we don't use a critic-aware learning, sometimes it will, when we train a bit, it will drop dramatically because it's not quite stable to train the actor in the high-dimensional space. But by using if you carefully tuning the actor, you can eventually have a better score. We also have a bunch of different tricks. If you are interested, you can have a look at our paper. So when we come to the experiments, we test our algorithm on 4 different WMT datasets and use a standard test and the dev set to train and to test it. And we use BPE and we use the maximum length of 50 symbols for MLE training and 200 symbols for the trainable decoding. And for underlying MMT, we use a standard 1-layer attention-based model. And for the actor, we use only 2-layer feed-forward network. In it, only 32 units are the hidden state. And for the character, for the critic, the variant attention-based model we use to predict what reward. And for the reinforcement learning part, we use ARMS probe as an optimizer, where we train 10 steps of the critic per 1 step of the actor. Because to train the critic well is more important than the actors, and it will make the actor more stable. And if compared to training the whole model, it will be very fast. Here we use 2 different objectives. One is the blue score, and then the one is the perplexity. And here we're just using 2 of them, but we can use any kinds of objectives to evaluate the model. Here the other 2. There's one figure here is showing the y-axis is the change of the blue score, and the x-axis is using different decoding objectives. You can see clearly that if our objectives is to improve the blue score, then we can find the improvement on the blue score. But I'm sorry, the figure just split. But you can see for the change on the perplexity will drop. On the other hand, if we train based on the perplexity, most of the model will improve on the perplexity. But the blue score sometimes will also drop. These scores are tested on the grid decoding. We also test the score on beam search, and similar things happens. So it shows that when we choose different objectives, the model will favor to decode in different ways, and based on that objective. There are some examples. So we can see that by using the trainable decoding, the model tends to to find some decoding errors. For example, for the example B, the model is trying to recover the original translation from the wrong way to the right way. Here we use the pink color to show that when the action, the value of the action increased suddenly. So normally the action will be just very small, but when there's something error happened, the model knows, okay, I need to bias the output, then to have a different decoding results. And thanks for your listening, and the code and the repo's data set will be found on this repo, but maybe in 2 weeks.
Thank you. So Joe had requested a minute silence for his rejected NIPS paper, but I suggest we go straight to questions. Questions? Questions?
Hi, thanks for your talk. So what are the absolute blue scores for your
Yeah.
how does it compare to the paper that was rejected, sadly?
No, yeah. The absolute boost score can be found on the paper, the caption part. So you already put it on that, yeah. So because the slides, we cannot put everything on this.
Thank you. So on the first slide, you had a nice breakdown of various other things that could improve the quality of machine translation. And the first one was modeling. And you're focusing on decoding. I was wondering if you have a sense for the headroom in terms of improving decoding versus improving modeling. Are the current errors coming from bad models? Because if they are, then getting a better decoder can help you a little bit, but still the fundamental problem is somewhere else, right?
Yeah, yeah.
So I was wondering if you have a sense for that distribution of errors, search errors versus modeling errors.
Yeah, that's a great question. Yeah, we didn't do such a different model, trying different models to see different ways. Definitely, if you have a better model, you'll have better scores. So our research is just to have a fixed model, which is standard model we widely used in other tasks, and then to see if our algorithm can improve it. And for the future work, you should try different state-of-the-art models and apply the same algorithm to see if it can improve constantly. Then we can make sure our model is just additive to different models. Yes.
Last question.
Hi, thanks for the talk. Could you give more intuition about adding the additional vector? Like, what's the difference between training the model just with the actor critic algorithm and with the added vector phi, or how was deciphered that?
Yeah, I mean, our intuition is we train a model whatever you use to train it, and we can always add a new module to control the decoding of that. So that is additive. We can always replace it by another one to do different things. We don't want to fine-tune different models for different objectives, and we need to save them everywhere. So this is a thing. And the second, I think additive is the most intuitive way to do this, because yeah, and
Okay, thank you.
thank you.
Okay, well, let's thank our speaker, and that